Greetings from Goshen, general physics students. I hope this video finds you all in a safe place, keeping yourselves healthy. And maybe this brings you back in the mind of when you were attending class in this very room. You're all sitting in the spot where Isaiah and Chrislyn normally would sit. So you've got a front row seat for everything here. My plan is to start right now with a little bit of a review of the lecture I already gave, and then to go on into the rest of week 9. It'll be in several parts. And then at the end of that, I'll have also some brief videos that will give you some helps for particular problems on WebAssign that might be especially difficult. In addition to that, we'll have some online Zoom sessions or something like that. But let's carry on. Let's take a look at what we already did back a little while ago, remind you how this all began. So I did some demonstrations where, in fact, you did this in lab as well, where you passed a magnet through a coil and you got currents to flow in various situations. And that led us to this interesting formulation. First, we had a definition of what flux is. Flux, and this is magnetic flux. And magnetic flux, given by this Greek phi, is just the integral of B. I'm going to write it as the perpendicular component of B times dA. And you do that over some surface. The surface is bounded by the loop that you're calculating the magnetic flux through. So you've got some loop like this, and you figure out how much magnetic flux is going through that. You take the B field times little pieces of area everywhere. It's only the perpendicular component of the B field that matters. In most situations, we'll actually be just taking B times A. That's the way it'll end up being most of the time. But if there's an angle involved, then you have to look at just the perpendicular component. And if in some weird case the B field would vary, then you have to go back and integral. I think there's one, you have to do the integral. There's one case in WebAssign where you have to do that. Then this is related then to if you find, maybe you measure on here with a voltmeter somehow like this, measure the voltage on this loop. You'll find that an EMF is generated, but it only happens when there's a change of some kind, when something about this is changing. And that is where we came up with Faraday's law. Faraday's law says that the EMF, this is the electromotive force, which is not an electric field, and it's not a force, and it's not energy, it's not any of those things. It's more like a voltage, except that it's a voltage that's sort of distributed all around here, and you could connect the loop and not have it be anywhere in particular if you had just a closed loop. But it's sort of like a voltage. The EMF is minus the change in flux. The rate of change in the flux is what determines the EMF. And then we talked a little bit about Lenz's law, and Lenz's law deals with this minus sign in there. It's sort of, that minus sign helps us to remember that Lenz's law says that when you have a loop like this, and say you've got a magnetic field everywhere, and that magnetic field somehow is changing so that the flux through the loop is changing. Say that the magnetic field is decreasing. If the magnetic field is decreasing, then these X's are disappearing slowly. We're getting fewer of them. Then current would want to try to flow around this wire in a direction, which I guess it would be this wire, that would replace those, that would try to oppose the change. Since those are disappearing, then it tries to add to them. And so then you use your right-hand rule. You want to have your fingers adding to the field that's there. And so your thumb goes around this way. And we would expect current to flow around that way while the flux is decreasing. Current would flow around that way. That would be true if this was shorted together, or if there was a resistor or something so the current could flow around here. If no current can flow, and you just have a meter on there, and you wonder which one is positive, then you have to remember this EMF is like the battery. And so in a circuit like this, current flows toward the positive terminal in the battery part of the circuit, and then it flows from positive to negative. So these would be this way. The lower one there would be the positive one, because the current is being pumped by this toward the positive terminal, and then out here it can sort of fall from the positive back to the negative the way it usually does. So that's Lenz's law. Lenz's law sort of helps us remember which way it goes, and it's this idea of opposing. It only opposes the change, and it opposes the change within the loop. Outside the loop, it actually helps the change, I guess you could say, or increases it. Okay, that is sort of a recap of what I already did, and then we'll move on to some of the next sections.